Yeah, so this is one of those talks where I gave the abstract a few months ago, and I was very optimistic that I would give some great survey of lots of things, and then, of course, reality increasingly sets in, and you realize how little you can say and how little you can understand. So it's a talk about F gauges, and I'm going to kind of tell you very briefly about some applications, but more it's going to be probably giving some very basic stuff about the picture and how it works, and maybe some hint of how to use it in some simple case. So this is, for those who don't know, it's a theory due to Bhatt and Lurie, Bhatt and Jacob, and also kind of somewhat independently to Drinfeld. And if you want to read a lot about it, Bhatt has notes on his webpage from a course he taught on it. And there's a vast number of applications and details and so on there. And so yesterday morning I was rewriting this talk to hopefully make it more accessible and maybe even fit into the time. And I remembered a book review by Langlands, I'm sure some of you have seen, which starts with the first sentence being, this is a shallow book on deep matters about which the author knows next to nothing. So if you turn that into a talk, that's what you're going to get. So I just want to start with one motivation for F gauges. So there are several. I think originally probably a motivation was prismatic cohomology, which I will mention a little, but not very much. I'm not going to assume anyone knows anything about that. There are all kinds of motivations in topology, things to do with K-theory, symptomic cohomology, theory of motives, and so on. And I'm going to say nothing at all about those. But you can see things in Bhatt's notes. So the motivation I want to talk about is what is the kind of right notion of good reduction for p-adic Galois representations. So kind of a simple example is to take an elliptic curve over Q. And this is a kind of historically also a motivation for some of the things I'm going to say. And associated to this, you have this is rho E, a Galois representation. So my notation for absolute Galois groups is going to be G sub the field. So this is the Galois group of an algebraic closure of Q bar over Q. And the representation is, well, let me start with a representation to GL2QP that you could obtain either by thinking about the p-adic tape module or kind of dually by taking the first total cohomology of E base change to Q bar. So this is some kind of important thing in number theory, studying these representations. And famously, there's the work of Wiles and Taylor-Wiles and Breuil-Conrad, Diamond-Taylor, proving the modularity of elliptic curves. And the way it's both formulated and proved goes via these Galois representations, which determine the elliptic curve up to isogeny. So good reduction for an elliptic curve is something very simple. You're just asking that you have a kind of nice model over ZL for some prime L. And if L is not equal to P, then there's the Neron-Ogg-Shafarevich criterion, which says that E over QL has good reduction if and only if the restriction of the Galois representation to a decomposition group at L is unramified. And that's very much not a correct statement if L equals P. So if L equals P, having good reduction, the Galois representations are never unramified at P. But, sorry, GQP, the correct thing to say is crystalline. A notion introduced by Fontaine, and this is something in general, if you have a smooth and proper variety with over ZP, say, then the Galois representation, the Galois representations given by the Étale cohomology are all crystalline. And in this case, this won't come up very much, but maybe I'll just say that the Hodge-Tate weights are 0 and 1, or maybe 0 and -1, depending on your choice of sign. So, and this theorem here, that this equivalence is due to Coleman and Iovita. It's a sort of p-adic version of neural Shaffer-Average. So the difference, I mean, there are many differences between these two cases, but one big difference that really makes a practical impact on kind of using these representations in the Langlands program and so on, is that this notion of being unramified is a very robust one. In particular, makes sense integrally. I could also consider kind of any coefficients I liked. In particular, I could consider sort of mod p coefficients like fp, and I understand what it means for a representation to be unramified. The notion of being crystalline does not make sense integrally. In some sense, that there really is no good notion of a mod p representation being crystalline. Because, for example, you would want it to have the property that if you had a crystalline representation in characteristic 0 and you reduced it mod p, that was something crystalline. But we know that every mod p representation comes from something crystalline. And also you know that you kind of lose track of things like the Hodge-Tate weights and things when you reduce mod p, so it's kind of hopeless. So the fact that you kind of lose track of all the kind of interesting data you might like to remember suggests that really, if there is a notion of a mod p representation, for example, being crystalline, it's not a property, but it's a structure. So there should be some extra structure that you kind of need to carry around that knows more than just the Gauss representation, and that would be the notion. And one answer, as we will see in a little bit, I think kind of the correct answer to what the integral notion of crystalline is it should be coming from one of these prismatic F gauges. So kind of in lieu of doing what I'd originally promised and telling you about lots of applications in detail, I'm maybe just going to try and draw a diagram that encodes, lets me, I mean, it's not really much of a diagram, but lets me sort of tell you about a few applications that people have made of this and of kind of related ideas. So what's my picture? So here I want to write ZP local systems over the generic fiber of some x, which might be perhaps a p-adic formal scheme. And up here, I want to write something like some kind of Gauss representation, and maybe it's going to go to some ring R. So what this is supposed to be encoding is this diagram is two notions of families of p-adic Gauss representations. So this notion is the one where you're looking at kind of the base is getting bigger. So instead of just thinking about the Gauss group of QP, I'm allowing myself to think about kind of local systems over kind of pretty much anything. And here, instead of looking at kind of representations to QP or the integral versions with ZP or something, I'm really allowing myself to take much more general kind of coefficients. And so sort of over here, I'd be doing both in this picture. Now, the reason I think this picture will be a very useful one in a few years' time, but at the moment, kind of everything is rather concentrated on the axes and maybe even over here. But just for orientation, in case it comes up later, and also I think because this terminology is useful, this axis is sometimes called the Australian axis. And this one is the German axis. So this is some type. I think so, yes. So Laurent is responsible for this. But actually, at least for me, and I think for some other people, this is very helpful terminology, because you have talks on families of Gauss representations, and you really find that the speaker and the audience have different views or expectations on which axis they're on. And this makes it possible to remember which one's which. And I wasted some time when I was preparing this talk thinking about what labels you attach to kind of things, maybe like this point here, which is this kind of more classical thing, maybe the kind of setting of Fontaine's original thing, or more optimistically, you want to assign to something over here? Like what is either the intersection of Australians and Germans or the kind of product of them? So if you're bored in this talk, maybe you can answer that question. OK, so on this axis of things that are actually known about sort of applications of things like F-gauges, I think there's almost, it's not completely clear to me if there's anything, but I think there's a point that's basically the work of Kissin, who did something pre-F-gauges, but I think probably equivalent to a formulation in terms of F-gauges, although I'm not completely sure of that, when he gave a reproof of the Taniyama-Shimura conjecture, the modularity of elliptic curves, which was much more conceptual. And he needed to study exactly this kind of situation. And so he wanted to think about representations that should come from elliptic curves, or more generally from their kind of p-divisible groups. And he introduced, well, Breuil had made a kind of suggestion beforehand, and he used what are kind of called now Breuil-Kissin modules to study Gauss representations associated with p-divisible groups and what happens when you kind of vary coefficients there. And then down here, I mean, there's no kind of meaning to where I'm going to label my points. But again, a lot of the work that's been done is kind of in the p-divisible group type setting, where Hodge-Tay weights are 0 and 1. There's kind of a classification of p-divisible groups. And finite flat group schemes. Over very general basis, very general sort of p-adic rings as a basis. And so there's, I think the suggestion that this should be possible and should be an application of F-gauges is maybe due to Drinfeld. And then there's work of Zachary Gardner and Kirti Madapuzzi. They have a paper on the archive proving results about p-divisible groups. There's work with Akhil Matthew, and in fact, one excuse for not talking about this stuff in any more detail in this talk is that Akhil gave a talk at this same conference a year ago, exactly on these things, and there's a video on the conference webpage, which I urge you to go back and look at after this talk if you're at all interested. I hope I'm going to give some kind of introduction to the ideas there. And Shubhadeep Mondal and with Kirti, I think, I have a forthcoming paper doing kind of more general finite flat group schemes in this optic. And then there's applications of this to the study of Shimura varieties and integral models. I think there's a lot of kind of work that's forthcoming using some of this, but concretely at the moment, there's a paper of Naoki Imai and Hiroki Kato and Alex Yukis, which again you can find on the archive that studies this in some detail. I should say again, the suggestion that this the F-gauges could be used to study integral models of Shimura varieties is due to Drinfeld, who has a number of papers explaining this. And then there's also a kind of thread of work of more generally studying kind of what it means for a local system to be crystalline. And I want to say, and there's a kind of a variety of papers here, many of which are Haoyong Guo is a co-author of, with Shizhang Li, Emmanuel Reinecker. I mean, I don't think it's compulsory that you have to be either German or Australian to work in these areas, although I guess maybe in this point, maybe literally true up till now. Zhishan Yang, and most recently, Maximilian Hauch, who probably is German, I think. So, OK. So before I forget, not going on this picture, but related to the things I said I wasn't going to talk about algebraic topology, as well as Akhil giving a talk last year. Ben Antio gave a talk more about kind of applications in algebraic topology. It wasn't maybe literally about F-gauges, but was using kind of symptomification in some sense, and I think the papers do indeed use the language of F-gauges. So that was about joint work with Achim Krause and Thomas Nikolaus. So that's also a very good thing to go back and watch. Okay, so that was possibly the extent to which I'm going to be surveying applications. I mean, I should say that we certainly expect and hope that there are more applications on these other axes, but I feel like that's still in the future. And in this talk, I'm now going to kind of very briefly tell you the kind of sort of big picture of what an F-gauge might mean in some very formal way. Then I'm going to give you some concrete definitions, and then I will hopefully discuss one kind of new application kind of at that intersection point of the German and Australian axes. So I should make a quick warning that in the theory, there's a lot of use of derived algebraic geometry and so on in the definitions, and I'm going to completely ignore that and sort of other technical hypotheses in everything I say. So I'm going to say a bunch of things that are probably not literally true. But so in some sense, everything is always derived when I say it, but I'm not going to write things as if it was. So hopefully that doesn't bother people too much. So X is a p-adic formal scheme for me. And at some point, it will literally just be spoof of ZP. And associated to this, by Bhatt, Lurie, and Drinfeld, are kind of three formal stacks over spoof ZP called X prism, Xn for Nygaard, so X Nygaard, and X syn for X symptomic. And so these are all stacks over spoof ZP. And I'll be able to tell you the definition of this one and say something about the definitions of these ones, assuming I don't totally mismanage my time. And I will also write sometimes R prism and so on for spoof of R prism. So for example, ZP prism will come up a lot, and similarly ZP syn and so on, and those are just spoof ZP syn and things. So this is functorial in the sense that if I have a map from X to Y, then I get maps X, F, up a prism between, I can't write a Y, X prism and Y prism and so on. Similarly for the Nygaard and symptomic versions. And we'll see a bit later that this X prism, as the notation suggests, has a lot to do with prisms in the sense of prismatic cohomology. And so one point that comes up, and one motivating idea, is that ZP prism, spoof ZP prism, is some kind of moduli space of prisms, and so it kind of knows all about prismatic cohomology. So I'm not going to say much about prismatic cohomology, but let me just draw a very quick picture. So this functoriality means I always have a map from any X, lives over spoof ZP, so there's a map X prism to ZP prism, and then given some point of this, some map from some spoof R, some p-adic formal scheme, maybe I'll call this rho R, I can do the following construction. Well, this thing has a structure sheaf, kind of OX prism, and I can push that forward to get pi lower star OX prism, and as always, this should be some derived push forward. And then you can pull it back over here to get some object rho R upper star pi lower star OX prism. And this is something that lives in the probably some p-complete derived category of R modules. And so this is some kind of just abstract-looking thing that one can do. But the point is, and this is part of the point of prismatic cohomology, is that just choosing different R's here is giving you different cohomology theories. If you like, you're literally starting with an X and outputting some kind of complex. And this encodes all of the cohomology theories that we know for p-adic formal schemes and so on. So you get different choices here give you sort of the de Rham cohomology, crystalline cohomology, Attal cohomology, and of course, prismatic cohomology. But I'm not going to talk about, the emphasis today is not about prismatic cohomology, it's about this kind of notion of good reduction. And for that, I want to sort of restate a result of Bhatt and Peter Scholze on a classification of, well, not just crystalline representations, but lattices in crystalline representations. So we'll see a bit later that on these stacks, well, on X prism, there's a Frobenius. This is some Frobenius lift of the kind of obvious Frobenius mod P. And there's also an ideal sheaf, maybe I'll call it I, which is what's called the Hodge-Tate sheaf. And using these two things, you can define what a prismatic F crystal is. So an F crystal, a crystal is just a sheaf on X prism, and an F crystal is a sheaf with some Frobenius structure. So it's E, a sheaf of OX prism modules with, well, not literally a Frobenius structure, maybe a Frobenius kind of structure up to isogeny. So kind of after inverting this ideal sheaf, I have some isomorphism of the Frobenius pullback with the original sheaf. And I will be making all these things more concrete later. I just want to kind of explain the picture. And then the theorem, sorry? Thank you. Yes, 1 over I. That would have been a bit of a nonsense definition otherwise. So the theorem of Bhatt and Scholze. So I'll state it. So I'm kind of sticking to, for the most part, talking about representations of the Gower group of QP, and thus talking about ZP. But this theorem is also true, the obvious variant, if I replace QP with any finite extension. So there are kind of equivalences, very natural equivalences, between ZP lattices in crystalline Gower representations, so crystalline representations of the absolute Gower group of QP, and these correspond to vector bundles. So F crystals, they're actually vector bundles. So vector bundle F crystals just over, sorry, not spuff ZP prism. My notation is just ZP prism. So just taking X equals spuff ZP in that definition. And these correspond to something which I haven't said what it is, but reflexive F gauges. So an F gauge, in case I completely forget to define it at some point, F gauges are just quasi-coherent sheaves on X sin, this thing that I haven't defined yet, and so in particular ZP sin. And this reflexivity is just the kind of usual, in some sense, just the usual notion of reflexivity in algebraic geometry, except we'll see that when these objects are not quite Artin stacks, for example, there's something a little more general. And they're very natural, yeah, there are very simple functors here, just given by basically restricting to opens in here. So this is ZP sin. One way to think about it is that it's, which I learned from Bhatt recently, is that you can think of this as just being a compactification of ZP prism. So one reason you want to kind of not just be here, but be here, is that this equivalence is just on some abelian level. But if you start looking at X groups, which is the kind of thing you want to do if you're fancy and derived and so on, but also it's actually a thing you want to do if you're kind of very down to earth, and you want to just do things like deformation theory. So if you go all the way back to my motivation at the beginning, you need to compute tangent spaces, next ones, and so on. And the X here are not well behaved. They're not the right thing. They're kind of infinite dimensional and so on. And here you get the right thing. So this theory here, these F gauges behave very well on the derived level. It's really not just giving you an integral notion of being crystalline, but it's giving you one that works in the derived category as well. So this is not just some kind of nice language or anything. This is really a very powerful and useful technique. Not going to have time, but if you look in Bargov's notes, you'll see things, for example, a theorem of Bargov and Jacob, where they not only reprove Tate local duality in this setting with a very different proof that's much more geometric. You're actually looking at the geometry of this stack. But they get an integral refinement, and again, at the derived level. So it kind of gives a completely integral upgrade of some stuff that Bloch and Kato did with sort of crystalline, like these H1F groups and so on. I would give you some statement, but I'm already going to be kind of over the time I'd like to be. But already, just to emphasize, just for kind of rather traditional things like Tate local duality, you get a new and kind of powerful perspective and new results using these things. OK, so I think that's enough without giving some definitions. So my next thing is I'm going to tell you what these X prisms actually are. So for that, I will very quickly just remind you of what a prism is, or tell you if you don't need to have seen it before. There's a notion of a delta ring. And more or less, a delta ring is a ring with a Frobenius lift. So I'm going to kind of skip a detail here, which is what happens when the ring has p torsion. I'll say something verbally. So I'm just going to assume, when I make this definition, that all my delta rings are p torsion free, which they will be, the ones I tell you. So a delta ring is a ring R with an endomorphism, a ring homomorphism phi from R to R, kind of lifting x to the p, x goes to x to the p from, I'm writing this the wrong way up, but never mind, R mod RP. So in the p torsion free case, this is literally the definition. It's literally the definition in general if for you a lifting is a derived lifting. But where the delta comes in is you write phi of x, just by definition of what it means to lift something mod p, it's x to the p plus p delta of x. And in the p torsion free case, this just determines this delta of x. And then you can write out what it means for phi to be additive and multiplicative in terms of this. And there'll be some p's in front. And you just divide by those p's to get the definition in general. So for example, if K is maybe a perfect field of characteristic P, the vectors of K with its usual Frobenius is an example. And an example we'll see in a bit, we'll see repeatedly, is an example that comes up in the theory of Breuer-Kissen prisms. So you have a power series variable U, and you kind of say that phi of U is U to the P. OK, so that's a delta ring. It's a ring with a Frobenius. And then a prism is a pair A, comma I, so where I is an invertible ideal, so it's locally principal. And A is a delta ring, sorry. And you demand that two things. One, A is Pi adically complete. And two, you want P to be in the ideal generated by I and phi of I. That's maybe a slightly strange-looking thing, but I'll always assume that, in fact, that this ideal is actually literally principal, which you can arrange Zariski locally. And then in this thing, equivalently, this just says that delta of D is a unit. Straightforward exercise. And just think it's an element of my ring, so that the ring is P, D adically complete. So D is topologically nilpotent, but delta of D is a unit. Okay, and then the idea is that these prisms sort of classify p-adic cohomology theories. And thus, by what I already kind of said earlier, those are going to be more or less classifying points of this ZP prism. So ZP prism is supposed to be defined in such a way that its points are sort of prisms. So we'll see what the definition is in a moment. But firstly, maybe I should just give you a couple of examples. You could take D to just be P and your ring is p-adically complete, because delta of P, if you just look at the definition, it's, I guess, 1 minus P to the P minus 1. And since P is at least 2, that's a unit. And the one that we'll be using a bunch today is the so-called Breuil-Kissen prism. So the same ring as up there. And then you take an Eisenstein polynomial E. So this is an Eisenstein polynomial giving some uniformizer of some field. But for example, in particular, I'll often specialize to the case of ZP. And maybe I'll literally take my Eisenstein polynomial here is just E plus P times a unit. And so I'll usually take U plus P. And again, you can just think for yourself why delta of this is always a unit. But for example, here, I mean, for U, I said that phi of U is U to the P. So delta of it is 0, and then you just get delta of P, which is the same thing. So this is another example of a prism. OK, so there's a very kind of general example of a delta ring, a ring with a Frobenius lift, which is a ring of Witt vectors. And I definitely don't have time to give a detailed overview of Witt vectors in general, but I just want to say something very briefly, because at least if you're me, before studying any of this, then the kind of Witt vectors you're used to are things like the Witt vectors of FP being ZP, so putting in some perfect field. But now you want to consider the Witt vectors of just any commutative ring. So all my rings are commutative. R is a ring. And then you can always form, and these are the so-called P-typical Witt vectors. For me, that's the only kind of Witt vectors. And kind of the underlying set is just kind of R to the a sort of product over copies of R indexed by the natural numbers. So you just have sequences x0, x1, and so on, the xi in R. But the addition and multiplication are not the usual ones. They're given by some kind of formulas that you'll recognize, but I'm not going to go into, just for reasons of time. I just want to mention, I mean, a lot of the things that you have for the Witt vectors you kind of already know are here. So you have things like you have a multiplicative lift, which is just the map that sends x to x, 0, 0, all zeros. And there's some kind of map the other way. There's a map the other way that just sends sort of x0 just to forgets all the other coordinates. This is sometimes called the zeroth ghost map. And there's a Verschiebung, which is very simple to describe. It's just the thing that shifts you one to the right. I'm going to stop writing all these x0s to start with. You just literally shift. There's a Frobenius, which is more complicated to describe. It's a Frobenius lift. At the start, the very first term is, I think, x0 to the p plus p x1, and then dot, 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 dot. formulas get more complicated. And then you always have FV equals P, this kind of familiar thing, and you always have V is sort of F inverse linear, so you have V of fxy is x V of y. And similarly, F is a ring homomorphism, and F just on these lifts is just giving the piece power. But the one thing I want to caution you is that if the ring has characteristic P, so if P times R is 0, then you also have the other formula you might be expecting, that Vf equals P. But in general, this is not true. I think this is true if and only if P equals 0 in the ring. And I've probably given you enough formulas on the board for you to check that for yourself as an exercise. So this is the kind of thing to be cautious of. OK, so yeah, this F is a lift of Frobenius. It's kind of plausible from the start of this. And so in particular, these Witt vectors are examples of delta rings because they have a canonical Frobenius lift. But then the sense in which they're there's some kind of sense in which they're sort of universal for delta rings. They have some property that lets you relate general delta rings to Witt vectors, which is the following adjunction. And it's that Holmes, so if A is a delta ring and B is any ring, I have Holmes in delta rings from A to the Witt vectors of B is Holmes just in rings from A to B. So in other words, if I have a ring homomorphism A to B, and A has a delta structure, has a Frobenius lift, then it lifts in a canonical way to the Witt vectors of B. And I mean, this lift starts by sort of its kind of X mapping. I mean, let me just not have some letter for the homomorphism, but it's kind of X. Turns out the next term is delta of X, and so on. It's kind of an exercise to figure out what these things look like. And of course, the formulas get more complicated as you go across, but we'll really only care about these first two entries in what I'm about to say. And so now the idea is you're given the following exercise, you're supposed to write down what the moduli space of prisms is. I don't think I would succeed in this exercise, but there are multiple people who have done, namely, Barkov and Jacob and Drinfeld as well, kind of did this exercise. And the idea is that, the definition of a prism only makes sense on delta rings, and so you don't want to consider something in algebraic geometry is not a functor on delta rings. But using this, you can convert it to some problem in Witt vectors, and the Witt vectors are indexed by the usual rings, and so you can kind of hope to encode something. And you can make the following definition. I'll kind of say it with some notation that I'll then immediately define. So ZP prism, I'll start with, and I'll tell you what X prism is a bit later, is it's a quotient stack. It's something called W dist mod something called W cross. And so this is a quotient in kind of whatever topology you like. There's a risky topology, I think, is enough. And so what are these things, just as functors, for example? So this is supposed to be, this is a stack, a formal stack over spuf ZP. So I need to tell you, for its functor of points is sort of defined on something that some people call nil, I think, or nil sub P, which is kind of rings in which P is nilpotent. And so given such an R, I need to sort of tell you what W dist of R and what W cross of R are. Well, W cross is easy. It's just things in the Witt vectors which are units. And you can convince yourself that's represented by some scheme. You can write down exactly what that is. And WDist, the dist is short for distinguished. And these distinguished elements are ones to do with prisms, we'll see in a second. And so WDist of R is the set of x0, blah, 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 in the bit vectors such that x0 is nilpotent. These xi's are in R, and x1 is a unit. And kind of, if I take some D in this set, the relationship, or a relationship with prisms, is that this implies that D gives you a prism structure on the bit vectors. And if you go back and stare at the definition, you'll see that the converse is true, except that we put a slightly stronger condition here. The definition kind of only required this x0, definition of a prism would only require x0 to be topologically nilpotent, and here we've changed it to nilpotent, so it's a minor change. Yeah, okay, this is not literally true, because maybe if I am allowing animated prisms or something, it would be true. But yes, it's not literally true. Kind of, there's a slight lie here. Maybe more than one. I just want to say that this thing is some kind of rather mild formal scheme. So it's represented by, you can take the ring, I guess you have variables A0, A1, which you invert, and so on, and you P A0 adequately complete it. So again, it's something quite concrete. So I'm just doing, it's a quotient stack of two kind of rather nice affine things, but maybe this is kind of, these are infinite dimensional. In particular, the thing you're quotienting by is not some sort of finite type group. But it's still something very reasonable. It's kind of close to the kind of stacks you know and love. And there's an action of Frobenius on this thing, just because there's an action of Frobenius on the bit vectors, and you easily check that it induces an action here. OK, so that's some definition, and it has some property that it's to do with prisms on the bit vectors at least. But in fact, it tells you about prisms in general. So given any prism, I can make a point of this stack as follows. So if I have a prism, I'm going to always be a principal ideal, A comma D, then I actually get a map from spf A to ZP prism. And what's the construction? Well, I have to sort of tell you what happens on the functor of points. So I have to say what happens if I take any spec R mapping to this, where R is P nilpotent. And the construction is just, I have to give you sort of an element of the bit vectors of R. And so I use the adjunction we had above, where I have a map. This gives me a map A to R, and that lifts to the bit vectors of R, and I just see where D maps to maybe something I could still call D here. And I raised the formula for the adjunction, but it started with sort of D comma delta of D, and D has some nilpotence property, and delta of D is a unit, and so it gives me a point up there. So given any prism, I have a map like this. So that kind of goes back to the thing I wrote at the very beginning. Not the very beginning, but about 20 minutes ago. I had a picture of pulling back to get cohomology theories, and now to get cohomology theories, I just have to write down sort of some of these distinguished elements. And maybe let me just very briefly tell you kind of two that you will see. Just, I'm not going to use them, but you'll probably see these if you look at any of these papers. There's two very natural choices of things over ZP. given by taking D to be either, well, P, which we saw above, at the beginning is giving us a prism structure. And this is called the de Rham point, to do with de Rham cohomology. And there's also a choice where you take V of 1, which is giving you, this is called the Hodge-Tate point, which is to do with that Hodge-Tate ideal sheaf. I didn't think I'm going to have much time. I don't think I should start defining X prism as well, but I can just tell you verbally what it is. A point of X prism is just the same thing as the data. Well, X prism is supposed to map to ZP prism, so it should give you a point of ZP prism. And then you just have a map from spec of the Witt vectors mod D to your X. And there's a caution that D needn't be a non-zero divisor, so really that quotient is actually some sort of mildly derived thing. That's really a sensible reason for me not to write anything about it. Okay, and then there's a fact, which is that sort of prismatic crystals, which we could just define to be, I mean, these are maybe quasi-coherent sheaves on CP prism by definition. These are called prismatic crystals. These are just the same thing as the data of a prismatic crystal in the sense you might have seen before, which is the assignment for each prism, just write A comma I, an A module called MA, and the kind of crystal part of it is that there's a natural kind of compatibility for any maps of prisms. There's an obvious notion of maps of prisms, and you demand that sort of the appropriate, I guess, sort of p-adically completed pullback is compatible. The reason this is kind of some kind of fact is that in general, this would kind of like literally be obviously true if all of the maps like this came from prisms, but that's not quite true. So there's some kind of cofinality statement here. And of course, the assignment is that I have some sheaf and I just pull it back to kind of these, maybe I should call this rho sub A. So rho sub A, alpha star of E. And so this is kind of the notion of prismatic crystal, or similarly, a prismatic F crystal is just one with this F structure that you see in Burger's paper with Peter and so on. And so in particular, kind of going perhaps down to something more traditional, a prismatic F crystal, as in the theorem I stated earlier, determines some kind of F crystal over every prism. Something we could call an F. I'm not sure if F crystal is really the right word, but what I mean is, given any prism, I get a module with a Frobenius structure, and in particular, I can use my Breuil-Kissen prisms. So a Breuil-Kissen prism like ZP prism U, E of U, I get the data of a Breuil-Kissen module. So that's a kind of an M, a module over ZP U, and an isomorphism of the Frobenius pullback with itself after inverting E. So this is notion due to Breuil and Kissen. And in the sort of case where this isogeny has kind of height 1, so it literally is a map from phi upper star M to M, and the co-kernel is killed by E of U, these are exactly the objects that Kissen used in the thing to start with. But now we have this structure for every possible choice. So I should say, like, there are infinite many choices here corresponding to different uniformizers. All these ones, different choices, and some kind of strange compatibility between them, which is slightly hard to write down explicitly and use, but is encoded here. And also you have these for all prisms. So there's something called the Q de Rham prism that I haven't written down.
But if you do that, you get what's called a VAC module. So basically, everything you ever saw in integral periodic Hodge theory is encoded in this one notion. And now you can make the same definitions over X prism, and you get the kind of things on this German axis from the start. OK, so I'm running down the clock in an annoying way. That means I'm afraid, fail to tell you what X Nygaard and X sin are, but maybe I can just say a couple of words, and you can ask me afterwards if you want me to show you a picture or something. But the Nygaard version is some version which, morally at least, is incorporating some filtration data into the picture. Similarly, it still has a moduli description in terms of Witt vectors, but it's kind of harder to understand. It's a little mysterious. And then the symptomic version is then easy given this Nygaard version. It's just given by sort of gluing two copies of X prism that live inside X Nygaard together, and the gluing involves a Frobenius. So you end up with some nice picture. But I think if I want to state a theorem and show you something, I can't draw that picture right now. So I want to just tell you an actual result that's new, and maybe kind of sketch extremely briefly how it's proved. And it's something, the result that could have been found and stated 20 years ago. So this is a theorem of Bhargav, me, and Mark Kissin in progress. But we are writing this at the moment, so hopefully soon. So let me take crystalline Gauss representation, and maybe I can now give myself QP bar coefficients. And then if you choose a lattice, inside this you can reduce mod p, and I'm going to choose my lattice so that this is semi-simple. I'm computing a sort of semi-simple reduction of this representation. Let's suppose this has Hodge-Tate weights h1 equal to hn. Then there exists a Brody-Kissin module for any choice of this uniform formalizer, any choice of this E of U. I have a Brody-Kissin module M, whose, sorry, these should be QP, sorry, whose corresponding kind of Gauss representation, the Brody-Kissin module turns out to be enough to already know the semi-simple Gauss representation. So this M, the associated Gauss representation is this rho bar, and such that, well, the data of this M is, the data of this Brody-Kissin module is just a free module, that's fine, and some kind of isomorphism after inverting E of U. This thing is, maybe I should put an FP to just say everything's in characteristic P here. And when I choose a basis, I can choose a basis so that the kind of, this phi is given by a matrix of the form sort of U to the lambda 1, some diagonal matrix, lambda n, times W, where this is, I want to say this is a permutation matrix. And a permutation matrix is in quotes because this is just a matrix where I have exactly one non-zero entry in each row and column. But I'm allowed those entries to be in FP bar star, so I'm not assuming they're all 1. So just choose kind of n independent entries and put some scalars in them. And the Frobenius is this form. That's telling you not so much so far. This is true for any irreducible things, but there's an inequality, kind of the h's or at least the lambdas. So maybe if I assume that the lambda 1 greater than lambda n, this says that the sums h1 up to hr are greater than lambda. It's this kind of usual dominance order and they're equal if R equals n. So this is a statement that in the case that this representation is just the sum of characters, you may have seen me give a talk about this before. This was earlier work with Mark that also used F-gauges and so on in some way. The more general case does not follow from what we were doing before, and the proof does not use what we were doing before, but it's another thing with F-crystals that I'll tell you about, something about the proof in a second. But I should just say that from this, you can very easily read off what the representation is on inertia. So e.g., if n is 2, just to make everything very explicit, then we're saying that the restriction to inertia is either the omega is the mod p cyclotomic character, omega 1, omega to the lambda 1, omega to the lambda 2, or there's what's called a fundamental character of niveau 2, and I'd be getting some powers here. So I apologize if you're not a number theorist, or not a kind of number theorist in the same area as me, you might think, who cares? But I should say that this thing is kind of a thing that's very useful in Langland's program and so on. This is the kind of thing you really want to compute. This has applications to what's called the weight part of Sayre's conjecture. And I think this result is something really quite general. And even the n equals 2 case is definitely new. And even sort of specializations of the n equals 2 thing let you reprove some results about the weight part of Sayre's conjecture that were proved with very complicated calculations of Borel-Kissin modules kind of more easily. So I should say much more easily. I could also just allow, there's a kind of a natural version if k over qp is unramified. There's a kind of obvious statement. And there's also kind of an obvious analog. This W is sort of an element of a Weyl group where I replace GLN with any other connected reductive group and so on. And the proof, we prove those as well, and the proof is completely uniform. OK, so the thing that underlies this, the reason this has something to do with F-gauges is yeah, I do. Sorry. Misstated it. Sorry, thank you. The key statement, thank you, is that there exists a permutation. That was impressive. I thought I could not look at my notes. A permutation of these things so that h of the Hodge-Tate weights are congruent to these lambdas. Mod p. Thank you, Bhatt. That's the theorem I stated before was also true, but the proof did not need very much. So this is really a constraint, a serious constraint. And I have maybe 2 minutes to kind of tell you how we prove this. Well, I don't know. I think it would be dangerous to give myself imagine that I have more than 2 minutes. So there's a kind of very simple statement that underlies this. There's a statement that is the following. So given rho, by this theorem of Bargov and Peters, I get, or maybe even an earlier theorem of Mark Kissin, I get a Borel-Kissin module. Which kind of over ZP, and then I can reduce it mod P, and then go mod P to get some M. So this is any crystalline representation, any choice of this Borel-Kissin prism, I get a mod P Borel-Kissin module. And then the theorem is that this has, so again, this is Bargov, me and Mark, is that M has a kind of natural mu P structure. So this is some property that is very much not true for general Borel-Kissin modules, but it is true for the ones that actually come from crystalline representations. And I should say, I mean, I could make this explicit, but not in 1 minute. There's a proof of the same fact very recently by Hui Gao and Tong Liu, also kind of independently subsequently approved this by a method that is somewhat different, doesn't explicitly use F-gauges and these things and so on, but in some sense does, because it makes use of all the theory of integral Sen operators and so on that we kind of learned existed from these considerations. And their proof you can see on the archives. They updated their paper maybe last week, and so if you look at their most recent paper, you can see this. And so what do I mean by this? What is this mu-p structure? Well, let me just very briefly say kind of a theorem that we proved that implies this, is that the Broglie-Kisin modules were coming from taking prismatic F crystals on this ZP prism and putting them back to the point I had from the Broglie-Kisin prism, which was something with spoof ZP double brackets U. Now I'm looking mod P, so I'm putting this FP double brackets U. And what we actually prove is that this map here factors through its quotient by a mu-p. So there's a mu-p action on this, and we prove the existence of a factorization. And the way that mu-p acts is very simple. So not just, if I look at sort of functor of points, I want to tell you how ZP is acting on sort of R double brackets U. R is as before. And then I want an action of mu-p. And it's just given by sort of ZP acts on U by multiplication. So it goes to ZP times U. And similarly for the higher powers. So I'm conveniently exactly out of time, so I'm not going to tell you the proof, in fact. But I should say that I'll make a couple of quick remarks. I mean, one thing is that the proof of this is like 2 lines long, and you just use the functor of points. I mean, maybe ambitious exercise, maybe not that ambitious, but exercise, once you know this is true, you can literally, it's an exercise in the bit vectors that I was writing down before. But it's using something. This is so one reason I think that I mean, we suspected this statement was true for a while, but didn't prove it, even though it's a very short proof, because it felt like it should be something, because it was true for all the Broglie-Kisin prisms, it felt like really you're saying something very general and you're actually kind of doing some descent for all prisms. But in fact, it seems really quite specific. So it's using rather crucially that the Frobenius on the Broglie-Kisin prism is raising U to the pth power and not something more general. So, I mean, I'm not sure I can disprove that there's a factorization like this for the Q-de-Rham prism or something, but we don't think there is. And I should also say that, yes, if you go away and manage to reconstruct that proof, you can then kind of guess that there are much more general things, and we do indeed, I didn't define them, but we have versions of this for the kind of Nygaard and symptomic thing, stacks, we have integral lifts and so on. So if you have a little patience, hopefully in a couple of months' time or so, we'll have a paper that kind of explains this kind of thing and some applications. And also, last thing, given this thing, the proof of this is sort of group theory, in quotes, and it's sort of some messing around in F and Grossmanians, but it's really, you have this Frobenius descent, and then we just do some kind of things that would be very familiar to people on that German axis. But now I'm really over, so I'm going to stop.